External angle theorems and tangents is the topic we're going to be working on today, and this is exercise 10b. There are three different theorems we're going to look at today. I'm going to prove the last one, but make sure you draw these somewhere or write them down. The first theorem involves a tangent. So the tangent, remember, just scrapes the circle circumference once, and we have our radius. So from the point on the circumference to the center. These two will always meet at the circumference at a 90-degree angle. So in this case, officially it says the radius is perpendicular to the tangent at that point of intersection on the circumference. So you could write this basically just as the radius is perpendicular to the tangent. Use your explanation to help you remember what the theorem is. And then you can make it shorter and shorter as you remember it. So B to A, and it extends all the way through. We also have another tangent, B to C, which also extends all the way through. So notice these two tangents meet at the point B. So from that point B to where they touch the circumference only, those two lengths will be equal. So tangents from a point to a circle are equal in length. Just make sure you stop the length at that point where they touch the circle and to the point that they intersect. You can just write this, basically it's just tangents at a point is enough. The last theorem is called our alternate segment theorem, and this is a good one. So if we look at the last diagram, notice again we have our tangent, but we've also formed a triangle inscribed in the circle. So remember, inscribed means it touches the points on the circumference. And we see that our angle exterior next to the tangent is equal to the opposite interior angle of our triangle. So just make sure it's the opposite one. So like you're peering directly across from X to X. Now I'm going to prove this one, but the very simple way to write it is AST. That's all you need to do. All right, let's prove our alternate segment theorem. The first thing you have to do is draw your circle. Draw in a triangle and draw in a tangent, making sure the tangent and the triangle meet at one point on the circumference. Now the hardest part is getting your tangent to actually touch the circle here. Okay, that's a little bit better. I'm going to put in some points as well. So A and B are just going to be points on my tangent. P is going to be the point of intersection, and C and D are the other points on my triangle. So the first thing you prove, as always, is state what you're trying to prove. So I'm trying to prove here that angle X and angle A are exactly the same. So I've put them in green, just so we keep that in mind. So here's my origin. It's only approximate, and it doesn't really matter where yours ends up in relation to the triangle. I think it all works out the same. So let's draw in our angle COP. Now there are a few things that I know about COP. I know that it's isosceles, right? Because CO is equal to PO, the radii of our circle. So let's let angle OCP equal M. And let's let angle OPC also equal M. Now what else can you tell me? Well, I'm going to do something a bit strange here again and draw a line from O down to the point CP. And I'm going to let angle COP be 2y. The line I'm going to draw is going to bisect the angle O. So that means on one half of the line will be y and the other half will be y because I'm letting that angle all be 2y. And we're going to get back to this line later. But first, let's have a check. What else can I put in here? Well, what about angle OPA? What do you know about that? If we use our first theorem that we learned, angles from the tangent that meet at the radius, right, like this, will always be 90 degrees. So I know that m plus x in this diagram has to equal 90 degrees by theorem 1. I'm just going to draw this in again, maybe put a nice yellow box around it so we know that this angle here is the one that's 90 degrees. Are there any other angles with x or m that equal, say, 90 degrees? What else can you find here? This is where we come back to our line OE. So for isosceles and equilateral triangles, when you draw a line down that bisects an angle to the opposite, or I guess in this case, the base of our triangle, it will actually touch that base at 90 degrees as well, just for isosceles and equilateral triangles. So it's kind of like my perpendicular height here. And I think there's a proof for that theorem in your exercise book somewhere, or maybe the Year 10 book, I can't remember. Okay, now I can say, well, I know m plus y plus 90 in triangle EOP has to be 180 degrees, just because that's the angle sum. Something magical is going to happen now. So I have y plus m then is, well, 180 minus 90 is 90. Now I have two expressions with m and 90 degrees. So we have that m plus x equals 90, and I also have m plus y equals 90. What does that say about x and y? Well, they have to be the same thing, right? That means x has to equal y. So in my diagram, I'm going to rub out my y's and replace them with x's. So angle COE is x, and angle POE is now x. Okay, have you seen it? We're going to use a theorem that we learnt a few lessons ago. So notice that COP is double angle CDP. So angle COP is double CDP. Why? Because remember, angles at the center are double that of circumference. So if COP equals 2x, my angle A has to equal half of that, which is just x. Therefore, I can conclude that A also equals x. It's a great proof, huh? All right. Here are our questions that we're going to start with. So I've got level 1 and level 2 questions. And I want you to have a go first. Pause it, draw it, find out what alpha, beta, and theta are. So I'm going to use the alternate segment theorem a lot in this question. So remember, external angle from tangent to the triangle edge will equal the opposite internal angle. So I know that alpha QTS is going to equal the same angle as TRS, which is 68 degrees. One angle done. Second angle. Well, what about this 65? And I think that's gamma, actually. I'll have a think about it. So I know angle PTR, again by alternate segment theorem, is the same as TSR. So they will both equal 65. Now I only have one remaining angle to find, and that is beta. So you could do this either by straight line or the fact it's in the triangle. I'm going to use the triangle sum. So I know that we have beta plus 65 plus 68 will be 180 degrees. And so hopefully beta is about 46 degrees. And then we have found all three angles in this problem. So same kind of level here of difficulty. Let's try it. So I've got to find what alpha is. Notice that OTS is 90 degrees because we have that tangent and our radius. Okay, and then there's my reason. Tangent means radius at 90 degrees. That was theorem 1. I don't know why I put a 2 there. That's okay. But what else do we know? We know that the alpha plus 38 plus 90 has to equal 180 because I have the angle sum of a triangle, STR. Take everything to the other side. I'll get alpha equals 180 minus 90 plus 38. So alpha equals 52. And I've just highlighted there which triangle I was referring to. Okay, this one is has a little bit more information. So we've got to find alpha giving reasons. First thing I notice is that PR is going to be equal to PQ. Why? Because like we said, tangents that intersect at a point to their circumference respectively are going to be equal. Right, what else do you know? So I can find angle ROQ and the reflex part because I have angle RMQ. So this would be angle at a center is double angle at the circumference. But remember, they both have to be either to the left or to the right of their respective angles. So I have angle RMQ is 117. So the reflex part of ROQ would be 2 times 117. 234 degrees. And I'll draw this in here. Okay, well, now I have a revolution, right? I know angle ROQ, the obtuse part, would be 360 minus 234. Which is 126 degrees, so I add that in there. Okay, any last bits of information? Maybe you know that RO and QO are the same length. I'm not sure if that helps, but they are the radius. Oh, here we go. We have some other facts. We know that PRO has to be 90 degrees because PR is a tangent, RO is the radius, and tangents meet at radius at 90 degrees. I think where I'm going is looking at this quadrilateral and trying to find the angle sum. This can be the same as PQO and PRO. Both of these will meet their tangents at 90 degrees. Okay, now I have a quadrilateral PROQ. So the angle sum of any quadrilateral is 360 degrees. So I have alpha plus 90 plus 90 plus 126 is 360, and I can find alpha. So alpha, let's do the calculation. What should we get here? Final answer, 54 degrees. I hope that is correct. Alright, here's another one. This one's not too tricky, but again, there are a few variables in here. So I know that alpha is 50 because my alternate segment theorem. Yay, that was an easy one. Now I want you to have a look at the triangle UAT. This is going to be an isosceles triangle. Why? Because UA is a tangent, and that tangent length is the same length as AT. So remember, tangents to a point are equal in length. So that means angle AUT has to equal angle ATU. So both of those would have to be 50 degrees. And if I know the base angles are both 50 degrees, then I can find my angle A at the top. So beta, where angle A is, would be equal to 180 minus 50 plus 50. The same goes for this triangle here. So I know that triangle BUS is isosceles. Again, I have 70 as my main angle, so angle BSU and BUS are going to be equal. And they're both going to be 180 minus 70, all divided by 2, which is 55 degrees. Okay, moving on. Here's just a little challenge. I want you to figure out how to draw it. So again, before I do any more than that circle, pause it, read it, and have a go. So from A, outside a circle, a secant ABC is drawn, cutting the circle at B and C. A tangent AD touches at D. A chord DE is drawn equal in length to chord DB. CBDE forms a cyclic quadrilateral. Let's start one at a time. A secant ABC is drawn. So remember, a secant touches the circle twice, and it starts at point A given by the information. So I'm going to put in my B and C here, and because it's ABC, I'm going to do that order. A tangent AD touches at D. So I'm going to draw a line A to D, where D is the point that tangent just nicks the circumference. A chord DE is drawn equal to DB. So I'm going to draw DB first, and then draw a chord. So that just goes from one circumference point to another that are equal in length. Lastly, CBDE form a cyclic quadrilateral. So I've got to join up E to C to find my quadrilateral here. And that will hopefully help with a couple of questions in the exercise book, or the textbook rather. Okay, there's the drawing for that. So the lesson will be up, weekly challenge, resource book, you know what to do. And remember, laughter is timeless, imagination has no age, and your dreams are forever. Have a good one, team.